And this is our official start of data structures today, so welcome everybody. Today our plan is to go over a new concept called recursion and a new algorithm called binary search. This binary search algorithm is really, if there's one thing, like only one concept you take away from this class, it's the binary search algorithm. It is definitely the most important concept in all of computer science. It forms the foundation of basically every search engine. So whether it's Bing or Google or uh, any website really that you're interacting with, if it's a social media website like Twitter or Reddit or Facebook, how they're able to find your user profiles efficiently. Essentially every program on your phone and on your laptop or desktop computer are using binary search in probably hundreds of different locations inside of it. So it's absolutely foundational to sort of real world computing. I will talk about lots of detail about binary search, but the high level idea is that it takes or lets you find information really, really efficiently. And by efficiently, I mean log in time. And so we'll talk about like why that's really efficient here in a little bit, but it's basically instantaneous. Doesn't matter how much information that you have. So like Google is searching the entire internet, billions, hundreds of billions of web pages, and they do it in fractions of a second. And it's because of this binary search algorithm. Let's see, so today we're going to start talking about this algorithm, but because it's so foundational, we're obviously not going to be able to cover everything about it today. And actually kind of the remainder of this course, or at least the next 6 or 7 weeks, we're going to be sort of exploring different variations of this binary search algorithm and see different ways that it comes up. So it'll be kind of a big topic for us. Okay, I'm going to share my screen. And actually, before we talk about the material for today, I just want to go over that survey that I asked you all to fill out. So thank you for the 33 of you who did that. Based on this, I will adjust things a little bit going forward, but I just wanted to give you a sense of some of these multiple choice responses so you can see how other people are feeling about the course too right now. So in terms of lecture speed, looks like a vast majority of people are happy with how it's going, so we'll keep that the same. In terms of workload for the class, most people say it's just right, but there's this significant fraction here that says a little bit too much workload. And I do agree that this class has a large workload, and I'm really trying to be sensitive to that, especially with this sort of online, non-traditional kind of environment. But actually this chart has me really encouraged that typically for this class, when I ask this question, the response is about almost 50% saying that it's too much workload. And so for this semester, I've really tried to cut out as much stuff as I can that's on the lesser end of importance so that your workload is not too overwhelming. And so as an example of that, we're just talking about midterms here a second ago, but there is no midterm in this class. We'll just have the final at the end of the course. And one of the main reasons for that is to help reduce your workload in this class. I really can't reduce the workload any more than I've already done in this course. And the reason for that is one of the real big purposes of this course is to prepare you all for an eventual job at like a top tier tech company like Google, Facebook, Netflix, Microsoft, Amazon, any of those companies. And I want to keep you all on track for being able to do that should you choose to. And if any of the material that's left in the course I were to cut out, it would you would not be set up to be able to do well at, say, a technical interview in those companies. Some of the other material that I've cut out, I've sort of left in the course as optional extra credit. So every week so far, there has been some sort of extra credit available. I'll mention in a little bit, there's going to be some extra credit this week as well. And those extra credit opportunities come from the material that I've made not required for the course to help reduce your workloads. Yeah, so I just want to point out that I realize there's a lot of material in this course. It is a hard course, but I'm doing my best to make it not overwhelming. For this one here, how people feel about Git, I'm really pleased with this, that most or a big fraction of people think that Git is great. If you are one of the people who falls into this camp of thinking that Git sucks, I just want you to be aware that if you choose a software development career path or any career path where you're interacting with software developers, you will be using Git as on a daily basis. This is one of the tools that as a software engineer, it's just impossible to get away from. And I guess there are some alternatives to Git. So there's a program called Subversion, another one called Mercurial, another one called Darks. These are all version control systems that do the same thing as Git, but they work slightly differently. And I think the sort of community consensus is that Git is by far the nicest of all of these. Everybody's kind of moving over towards Git at this point. So it's the sort of thing that you don't have to love, but it is something that you do have to live with, because in the real world, everybody uses it every day. Vim is a different story. So personally, I love Vim, and among the programmers who I happen to interact with, Vim is by far the most popular text editor. But Vim is, if you don't love Vim, that's okay. Still going to make you use it for this course, but in future courses or in the real world, depending on where you're working, you might not be using Vim. Or if you're, say, working as a software engineer doing typical application development for, like, say, cell phones or iPhones or iPads, any of those kinds of where you're developing programs that interface directly with the user, it's very common for those sorts of programmers to not use Vim as your setup. If you're doing more back-end work, however, so like say working on Google and making their web search engine actually run efficiently, it's very common for that type of programmer to use Vim. Yeah, so the people who are doing more big data kind of analysis stuff almost always use Vim or possibly Emacs. People who are doing more front-end development use other tools. If you do go on to take the big data course here, then because of just the nature of big data, it really is like required to use Vim to solve those sorts of problems. So in this course, it would have been possible for us to have picked a different text editor like VS Code to solve our problems and work with. But one of the reasons why I'm forcing you to use Vim at this point is because once you go on to the big data course, it's actually just impossible to use VS Code to do that. As an example, in the big data course, one of the things that you have to do is you have to control remotely thousands of computers at once from your own laptop. So not just a single computer like the Lambda server, but thousands at a time. And without Vim, that's just impossible to do. Yeah, so that's just quick survey results. Thanks again for everybody for filling those out. And today our material, so it's been posted on GitHub under week 4, and we're talking about recursion and binary search. So I got a couple of comics up here to help illustrate some of the important aspects of recursion. And in this first one, you see that here's Winnie the Pooh, and then Tigger sees that he's involved with recursion, and he's freaking out. And one of the things about recursion that it's kind of scary to a lot of beginner programmers when you first see it, that it's very different than the things that the control structures we've seen before, so like for loops and while loops. It takes a little bit of wrapping your, just thinking in different ways. And so this sort of panic is something that happens a lot at the beginning to programmers. If after this week of working with recursion, you still feel that panic, that's okay. But hopefully in, say, a month from now, recursion is going to be something that's just second nature to you and as easy as for loops and while loops. If you if your goal is to get a job at a top tier tech company, Facebook, Google, Microsoft, any of them, then it's going to be expected that recursion is as easy for you as for loops and while loops. And a lot of the sort of things they focus on in the technical interview, they won't explicitly say they're asking a question about recursion, but you should expect that every answer is somehow going to involve recursion. It's sort of very, very fundamental. So yeah, kind of what recursion is when you reference, we'll see formal definitions and examples here in a second, but when you reference yourself from within yourself. So here, this comic has this comic embedded inside of it, which has it embedded inside of it, and so on, down out into infinity. A very common thing that the computer programmers do is we sometimes make what's called a recursive acronym. And the most famous recursive acronym is this one right here. This acronym, so some people, if you've only seen it written out before, you might pronounce it new or new, like the animal, the new, that's what it's named after. But as a recursive acronym in the computer programming world, we pronounce this GNU with a hard G. And so one of the ways that I can tell whether somebody is a sort of in the club as a computer programmer or not, as a real hacker, is whether they would pronounce this as GNU or as new. If they pronounce it as GNU, then that's a good sign that they're sort of a real hacker. And what this acronym stands for is GNU is not Unix. What this whole program is talked a little bit about the history of Unix kind of before, but Unix, again, 1970s operating system that's created and is sort of like everybody realizes that this is the right way to make operating systems. The copyright for the Unix system, or all the patents, expired in the 1980s, late 80s. And so a guy named Richard Stallman created this GNU project, which re-implemented all of the Unix operating system in an open source framework. And so that's why it's called GNU's not Unix, because it's not Unix, but it's kind of like Unix. And so it has to reference itself in its own name. And there's a famous court case about whether this was legal or not. And this cartoon just has some actual snippets that, like, the judge was very confused when the lawyers were trying to explain what this recursive acronym means. One of the requirements for this class in order to get an A or A minus is in the main page. There's a list of readings or videos to watch. Scroll down a little bit further. Right here, so these two videos or this reading right here. And the purpose of this is to give you a history of this GNU operating system and this kind of open source framework. So if that's at all interesting to you, then these are the things to go out about and watch and read next. Okay. So yeah, we're talking about recursion today. It's closely related to proof by induction. So if you've taken discrete math before, then recursion will seem very familiar to you. If you haven't taken that course yet, that's okay. You'll just, when you get proof by induction in that course, you'll find it's very familiar to recursion. And so one property of any algorithm is that it can be written either with iterations or written iteratively, and that means it's written using loops, for loops, while loops, those kinds of structures, or it can be written recursively. And again, recursively means you're calling yourself inside of yourself somehow. So what we're going to do next, and what we'll kind of spend most of the class today looking at, is a bunch of examples on saying examples of programs that are written using iteration and written using recursion, and seeing exactly what they're doing and how they're related to each other. So inside of the folder for the week, there's this file notes.py, and that's what we're going to take a look at next. I'm going to switch my screen over to the terminal here, and we'll try something a little bit different today. We'll do a top-bottom screen split instead of side-by-side. And let's take a look at this notes.py file. And here, the first sort of example program that we're going to look at is the factorial program. And factorial, so recall it's just factorial of a number is all the numbers between 1 and that number multiplied together. So the factorial of 10 would give you this number right here. And the very first homework assignment in this class, you saw an iterative implementation of this factorial program. For this program, we can also implement it recursively. And here is the recursive implementation. So notice that here inside of the function's name is factorial underscore REC, REC standing for recursion. Factorial underscore rec is called within itself right here. So factorial underscore rec. And there's two things that you always have to do whenever you're doing recursion. So two things you always have to do whenever a function calls itself from within inside itself. The first thing is that when you call your function, you must have some different value inside of here than what you had up here. And this value must in some sense be smaller. So here in this case, the value is going to be n minus 1. And whereas the input value is n. And here we have what's called a base case. And this is the second thing that you always have to have is a base case. And the base case will tell us when the program is going to actually stop. Okay, in order to see exactly what this function does and why it is going to calculate the factorial function, we're going to switch over now to Python Tutor, and we'll do just step-by-step through this program, seeing exactly what it's going to compute. So coming back over here, let's see. So here, I had the iterative version open in Python Tutor. Here we go is the recursive version. And so it's the same exact function that's in the notes, factorial underscore REC. And there's our, what we call the base case right here, and the recursive call right here. And we're just going to step through the program step by step, seeing exactly what happens. So this first line, we've defined this function, creates on, recall that this blue box right here is called a frame, and it's the original frame that you have whenever you start a Python program. It's called the global frame, and all of our global variables are defined within the global frame. This factorial underscore rec right here, this is the name of our function that we just created, and so we're not running the function yet, we're just defined it at this point. And now on line 12, when we run that, that's going to actually run the function. As soon as we run a function, it creates this new stack frame right here. So that's our new stack frame. So the sort of title of this frame is factorial underscore rec, because that's the name of the function. It has one parameter n, and that n value is equal to 5, because that's what I pass in right here. And I'll step through this. Here, this if statement, n is not equal to 1. So we're not in this if statement. We're going down into the else. And we're going to execute this line right here. In order to evaluate this line, in order to be able to do this multiplication, we first need to figure out what is the value of factorial at n minus 1. And so in order to do that, it'll rerun factorial. And so notice now it's created a new frame object down here. And this frame has n equals to 5 minus 1 or 4. So I'll go back, press previous. Here, n equals 5. So n equals 5 minus 1 equals 4. Factorial underscore rec of 4 is what we call. And so factorial rec n equals 4. Again, it's not equal to 1. So it comes down here. redo this line right here. Now it's 4, 4 minus 1 is equal to 3. Keep going. Now it's equal to 2. Keep going. Now it's equal to 1. And now we go into this if statement right here. So let's see. I'm going to pause here and just mention a couple things that are really important to remember. So notice now we have a whole bunch of these factorial underscore rec frame objects. This whole column right here, we call this whole column here the frame stack. It's a stack in the same sense of stacks that we saw before, because every time we call a new function, we push a frame onto the stack. So here, when I'm on line 10 right here, I'm calling this new factorial underscore rec function. And so I'm going to push a frame onto the stack. And in this case, the stack is kind of drawn upside down, where what we used to call the top of the stack is kind of on the bottom. But this is even though it's on the bottom, this is the top of the stack right here.
And Mike, when you say, sorry, when you say frame, you mean the function call, correct?
So I mean each one of these boxes. The box itself is the frame. The frame is associated with a function call, but the frame itself is just the collection of variables that are created when the function call happens.
Okay.
Let's see, yeah, so one of the sort of confusing properties of these frames is that when we have these variables, so we had all these variables here, and they all share the same name. But when we have multiple variables that share the same name in different frames, we only use whatever the frame is that's sort of the most recent frame, the one that's at the top of the stack, or the way this is drawn, the one that's in the lowermost position. The vocabulary term is that we say this, this variable right here, this version of n is the active version of n. These variable n's are shadowed. They are shadowed by this variable right here. And that means we don't have access to them. There's no way for us to see what these variables are. We can only see what this one is right here, the most recent one. This is another vocabulary word, is that we would say this is the variable that is in scope, and these variables are out of scope. In scope means that we have access to it. Out of scope means that we just do not have access to it. And so at this if statement right here, if n equals 1, there's only this in variable that's in scope, so this is the variable that we're checking. Any questions so far before we continue? Okay. Let's see, so I mentioned before that every recursive function must have what's called a base case. And this if statement right here is the base case of this recursive function call. And the purpose of the base case is to sort of stop the recursion from happening and say we're done doing recursion. And so in this base case, because n equals 1, when I go next, we'll come down here and hit this return n right here. And because we're on line 8, it means we're guaranteed not to go to line 10. As soon as we hit return, it means we're done with the function. The frame that was created during the function call is destroyed. It's popped off the frame stack, and control goes back to whatever the previous function was. So here we return this n value, and n equals to 1. So I press next, it says return value of 1. This return value of 1 will get substituted back for our call to factorial underscore rec in the previous frame. So I'm going to hit next, and you'll see that the arrows jumped right down here, and down here are factorial rec with n equals 1 frame stack got destroyed. So I'm going to go backwards again so we can see that again. And so here's the top of the stack right now. As soon as the return happens, we're going to pop this frame off the stack. Notice the return value is 1. Pop that off the stack, substitute the 1 right here for factorial rec n minus 1. So now this return right here, factorial rec n minus 1, that's equal to 1. Our n value is equal to 2. So 2 times 1 gives us a return value of 2. And that's why this is saying it has a return value of 2. Once again, we're hit a return call. It's a different return call than we hit last time, but it's still a return call. And so return says pop the current frame off the stack and give that value 2 to wherever you were called from. So hit next, pop that off the stack. This factorial underscore rec of n minus 1 gets replaced with a 2. So to the right of the star, to the right of the multiplication is a 2, because that's what the return value from the previous call was. The n value is 3. The n value is 3, so we get 3 times 2, and that gives us a 6. Once again, we hit a return, so the 6 so the whole frame gets popped off the stack, and then the 6 will get substituted in right here, where the function call happened. We have a 6, and we have a 4, n equals 4, n equals 4, factorial rec equals 6, because that's what the return value was. And so 6 times 4 is 24, and that's what we're going to return. One more time, we hit a return, so we pop this off the stack, returning the value 24. So 24 gets substituted right here. 24 goes here, n equals 5 gets put right here. 5 times 24 is equal to 120, and so that's what the return value of our original factorial rec of 5 is going to be equal to. It'll give us 120. And that's sort of the end of the program. Yeah, so key things to, let's see, maybe before I do a key things summary, are there any questions about what we just saw? Okay, so key things to take away from this example and to remember about every recursive function are, again, that when you're doing factorial underscore rec right here, you must somehow make your, whatever your parameter is right here, it must go smaller. And in particular, it must get closer to whatever this base case is. If we were to change this, so there's no n minus 1 right here, let's go ahead and see what's going to happen. So there's no n minus 1. Visualize that execution. And we'll step through it a couple times. And now you can see this n value is always going to be equal to 5. If we do a recursive call with the same exact parameters that we had as input, then we're always going to call the same exact thing over and over again. And so it's effectively an infinite loop that you can never change the value from one stack frame to the next. And so it's just going to keep pushing and pushing and pushing, and it'll never get a chance to pop. So that's the first thing. You must somehow decrease whatever it is, whatever the parameter is that you're recursing on. Make it smaller, get it closer to your base case. The second thing is that you must have a base case. Let's see what happens if we don't have a base case. So I'm going to comment out these 3 lines right here. And so we only have this recursion without a base case. And we'll visualize that execution. And we'll step through this a little bit. And you can see that the ends are getting smaller. So that's good. That's getting closer to 1. But now suddenly the numbers are becoming negative. That there's never a situation where it says, hey, we're done with the recursion and you can now stop. So this is another way that you can come into an infinite loop, or yeah, you come into an infinite loop with your recursion. You either do not have a base case, or when you're calling the recursive function, you're somehow not making it go down at all. So those are like, those are the key two things to remember about recursion as you're programming. Always, always, always make sure that the base case is there, and always, always, always make sure that somehow you're changing your thing that you're looping over so that it's getting closer to the base case. I've been saying that kind of we have to make it smaller, but there's no reason necessarily why it has to be like -1. In some situations, it could be +1. So if it's a number, it could be getting bigger. The key thing is that it's getting closer and closer to the base case. Any questions about this example so far? Okay. Let's see. Yeah, so this is an example of a recursive function that is sort of equivalent to this iterative function right here. There are, like I mentioned before, any iterative function or program can be written recursively, and any recursive function can be written iteratively. In this class, I'm not going to say, I'm never going to ask you to, here is a recursive function, implement it using loops. Or here's a function with loops, implement it using recursion. Instead, so that's something that you would do if you go on to take the algorithms course, CS 148. In this class, the real focus is just to sort of understand how recursion works. And if I give you some pseudocode that uses recursion, be able to translate that pseudocode into actual working code. For programs that, there's a really good question about like, okay, what's the advantage of recursion and what's the advantage of iteration? If I can always use both of them, when should I use one versus the other? And I've got a short answer for that in the notes right down here. That the advantages of recursion, there's 3 of them. The first one is that it's actually easy to prove that algorithms are correct using recursion. So computer scientists will actually sit down and write formal proofs about their algorithms the same way mathematicians will write theorems. Computer scientists will too. And it turns out to be really easy to do that with recursive algorithms, and really, really nasty and painful to do that with iterative algorithms. So sort of the more theoretically inclined a person is as a computer scientist, the more likely they are to use recursion for tasks. Something that we will talk about in this course, starting on Wednesday, is that it's really easy to prove the runtime of an algorithm with recursion. So we've talked about runtimes with algorithms that use for loops so far. For loops are pretty easy to do, but if there's a while loop is really hard to prove the runtime about, because there's no way to say exactly how many times a while loop is going to actually execute. But with a recursive program, we have this theorem called the master theorem that we can just plug it in, and it gives us the runtime piece of cake. And the last thing is that some algorithms, typically algorithms that would normally involve a while loop as an iterative program, are much, much simpler with recursion. But the disadvantage of recursion is that if you could use for loops for an algorithm, probably want to use for loops and not use recursion. Any questions about those advantages, disadvantages? Here in a second, we'll take a look at the binary search algorithm, which is sort of the classic example of an algorithm that's much simpler with recursion than it is with iteration. Let's see, yeah, so the textbook mentions these 3 laws of recursion. I sort of mentioned them before. Your recursive algorithm must have a base case, and it must somehow call itself with a smaller values. Those are key things to keep in mind. And I want to show you now what happens in Python if you break those rules. So we're going to come back over here, to the terminal, and let's see, so we have these notes. Let's just go ahead and run the doc tests, make sure that they are correct. Notes.py, okay, no output, that means the doc tests are correct. But I'm gonna go ahead and change this program in the same way that we changed the programs before in Python Tutor in order to break those laws of recursion and make the program run forever. So the first way that I did that was I did this right here, making the recursive function call itself without reducing the parameter at all, keeping the same parameter. And we'll see what happens. And what you get is this recursion error, maximum recursion depth exceeded in comparison. And anytime you hit an infinite loop using recursion, then you get this recursion error. I'll write that out. If you see recursion error in your Python output, it means you had an infinite loop or that you broke one of the laws of recursion. Broke one of the laws of recursion. And in this case, the law we broke was that we didn't make the in value smaller. The other way you could break the laws of recursion is that you don't have a base case. So if we take this away again, take away the base case like this, rerun these tests, and have valid Python code that actually runs, you'll see that we get the same error right here. Recursion error, maximum recursion depth exceeded. So if you get this error, there's no way to tell which law of recursion that you broke. There's no way to tell whether you broke recursion right here by not changing your in value, or if you broke recursion right here by not having a base case. You just have to know that if you get that, check both of those things, that's where your problem is. One of those two things. This, let's see, so in Python, the Python language for this error is a recursion error, but the sort of general computer science term for this is a stack overflow. We said before that that big set of frames that we were looking at in Python Tutor is called the frame stack, and every programming language has some limit on how big that frame stack is allowed to be. In Python, the default is about 1,000, and so as soon as you hit that limit, you have overflowed the amount of stack that you're allowed to use, and you get the stack overflow. If you've used the website stackoverflow.com to look up programming answers, that's where the name of that website comes from, is from infinite recursions that do not have a base case or do not decrease the size of their recursive argument. Any questions about anything so far? Okay. So then we're ready to start talking about search and doing it with recursion. So search, again, most fundamental thing to do in computer science. And there's two algorithms that we'll look at today. The first one is called sequential search, and then we'll look at binary search after that. So there's two differences between both of these algorithms. The first is in sequential search, it works for any input. So you give it a list, doesn't matter any properties of the list, and it's guaranteed to find the correct answer. The second property is that its runtime is going to be linear runtime. So anytime you see theta n or O of n, we call the runtime linear. For binary search, it has an additional requirement, requires the input be sorted first. And we will see next week, applying this master theorem, that the runtime of sorting is theta n log n. So it's a little bit expensive maybe to do the sorting, but once you've done that sorting, the runtime of the actual search itself is just log n, so really, really fast. And again, the logarithm, it's sort of unintuitive how small the log of a number is, but so the number of web pages on the internet in the say order of 10 to the 14, 10 to the 15, take the log of that and you just get 14. So it's only 14 instructions in order to search the entire internet. Okay, so we'll first take a look at this sequential search, and then we'll take a look at binary search. So here's our, we'll have two versions of this function, an iterative version and a recursive version. And in the iterative version, well, actually in both versions, our function takes two parameters, xs and y. Xs is the name, or is a list that contains the things that we're searching inside of. And the y value is a number that we're checking to see whether it's inside or not inside. This code right here is equivalent in Python to the code xs and y that we would call this just syntactic sugar. Again, syntactic sugar for this for loop right here. And all it does, loops over, checking every single element. If they happen to be equal, return true, otherwise return false. Our sequential search follows the same pattern that we saw with the factorial function that we had before, but now the thing that we're recursing over is not a number. The thing that we're recursing over is a list. So how do we make a list smaller? Well, we can use a sublist like this, xs indexed or subscripted from 1 colon. What this means is remove element 0, return all of the elements 1 and later. Let's go ahead and take a look at this inside of Python Tutor. So not that one. Here we go, this one here. And so this is the same sequential search recursive function that I had in the notes.py. And we'll step through this step by step to see what's happening. And so let's come down here, get into our recursive call right here and run it. And so our new stack frame has two variables, xs and y. Each stack frame is going to have these same two variables because those are the now two parameters to our function. So that's why there's two variables in the stack frame, two parameters to our function, two variables in the stack frame. Now this xs, this parameter that we're doing recursion on, I know it's the parameter that we're doing recursion on because this is the one that I'm changing every recursive call, is a list instead of an integer. And what we're doing to this list, we're making it smaller by actually removing one of the elements. So here we're doing xs1 colon, removes whatever in the very first position right here, gives us back everything else. Makes a copy of that, passes it to sequential search again, and goes through. So run it again, now with the smaller version of xs. Again, at this point, this xs refers to this xs, refers to this list. We do index at 1 colon, slicing from 1 to the end of the list, gives us all of these positions, 5420. Hit next, and here's our 5420. So now our sort of recursive law that the recursive variable must get smaller each time, the way we're implementing that is by having our list object here actually shrink each time, using a smaller list each time. And every time we go through, the list will get smaller and smaller like this. At this point, we actually have two base cases for this function. Here, the base case is these return statements that do not have a recursive call inside of them. So you're allowed to have multiple base cases. You just have to have at least one base case. And which the base case that we got caught in right here was this one, xs at position 0, is this 2 right here, checking to see if that's equal to y. Well, the thing that we're searching for is a 2, so it is in fact equal to y. So our return value is true. that return value gets passed up all the way through all of the previous call stacks, and so our final result is true. It's able to find that 2 is in this list. Are there any questions about how this sequential search is working?
So Mike, just to clarify really quickly, sequential search is just going index by index in the list and kind of matching what we're trying to find in the given list, right?
Exactly.
Okay, go ahead.
Hey, Mike.
Mhm.
I don't know if you were going to do this example next, but I'm curious to know when the y parameter is 6, how do we slice into like a list that doesn't have that?
Yep, great question. So let's do so this is our second doc test up here. The first doc test that we ran was with a 2, something that was actually contained in the list, so it was returning true. And the second doc test is a 6, something not contained in this list, and so it's returning false. In this case, you can sort of look ahead and see where the return value, where this false is going to come from. It must come from here. That's the only place that a return false can come from. And so we'll see that we'll get to this base case instead of this base case. So that's, in this particular algorithm, that's why it's important that we have 2 different base cases, because sometimes we'll return true and sometimes we'll return false. Let's step through what that looks like. And you can see here on each recursive call, when we're doing this XS sliced at 1 colon, the same exact thing is happening where we're taking off the, just going from 1 to the very end, taking off whatever's at position 0. That at this point, when we do the recursive call, we're not even looking at the y value at all. The only spot where we look at the y value is right here, this spot here. And so let's keep going and keep going. So because we're looking for 6, our y value is a 6, and 6 does not appear anywhere in this list. This if statement on line 11 is always going to be false, because no matter what xs is equal to, no matter which of these xs variables we look at, no matter what slice we're considering, the y can never be at the very beginning position because there's no 6 anywhere in this list. So that's why this if statement is always false. And we come down here, still false. And now down here, we have our XS is pointing to an empty list. So at this point, our XS variable has nothing in it, so it definitely cannot have a 6 in it. And so that's what kind of the intuition behind this base case. If there's nothing in the list, that means no matter what we're searching for, it's not in the list. And so we're safe to return false. And the length of XS equals 0 because it's an empty list. So the length is 0. So we get this return false here. It's going to return false in the frame. That return false will get passed up to all the recursive calls of the sequential search function, passing that return false up, and ultimately that's our final value false right here. So the key difference between these 2 values ends up being that the recursive parts happen exactly the same for both of these 2 function calls. It's just the base case is what works differently for the 2 of them. And that if it's contained in there, this base case will catch it, return true. If it's not contained in there, then this case will never happen, which forces us to go into this case and return false. That was a great question. Are there any other questions about that or recursion?
Yeah, I have a question. So I know that like the iterative and the recursive method in this case are both O of n or theta of n. But in reality, I was wondering if in this case the recursive would take longer time since it has to loop through every element in the list and then also go back to return false a bunch of times.
That's a great question. So actually this version of the recursive code is actually going to be n squared instead of n. And yeah, when we talk about the master theorem on Wednesday, we'll be able to formally justify why that is. But the sort of intuition behind why it's going to be n squared is that every time we are going from one step to the next down here, we're actually having to make a full copy of this list. So when we go from, like we notice that this XS here, it's not pointing to this list up here, like what would happen when we did XS equals YS, or when we just use the assignment operator. Here it's making a full copy. And because of that, it'll be n squared. Let's see, so part of the question was, because we're sort of going down the stack and up the stack, does that actually slow down the code at all? And the answer is that Python and it sort of depends on the exact implementation of Python that you're using, and more generally for programming languages, it depends on what the exact implementation you're using. But for most programming languages, what they do is they actually modify your program under the hood to be something equivalent but faster. And if it's ever the case that a recursive algorithm is would have been better implemented as an iterative algorithm, it will sort of rewrite it for you under the hood. So you don't need to worry about those sorts of, if the big O runtime is the same, then the actual runtime will also be the same. It's a great question. If the answer to that is kind of leaving anybody confused, then just know that we'll on Wednesday see the full answer to the question about runtimes with recursion.
Mike, about I think the last recursive call, how are we not getting like some sort of indexing error?
So when we're doing, say, this 1 colon on a list, like at this point right here.
Right.
Yeah, so one of the things about Python is when you're doing a slice like that, so if we say XS equals this, you can do that without an indexing error. And it's specifically built like this so that you can, to make like recursive algorithms a little bit easier to use. That if we did not have that colon there, we'd be out of bounds. But with that colon, it just says it's the empty list. It's a little bit of a confusing behavior of slices, but a great question. Any other questions so far? These are all great questions. Okay, so let's come back over to our notes. And I actually have a few different implementations of this sequential search recursive that kind of illustrate different techniques you can do when you're implementing recursion. And these are things that you will see me do kind of throughout the course. So the first one is creating a local recursive function. So we saw before that maybe 2 weeks ago now that you can create local functions in Python. So this function here, go, is only available from within this sequential search function right here. And the actual, in this case, this go function is exactly the same as the first version of sequential search. It's just at this point, instead of calling sequential search, it calls go. So this one is, the only difference is that we have a local function inside. But this sequential search 3 is a little bit different in a couple of other ways. So we still have this local function inside right here, but now notice that this local function is going to be taking in an integer as a parameter and not a list variable. And this is sort of the most correct way to do the sequential search as a recursive algorithm. And so I want to take a look in Python Tutor about this one and what's going on and why it's different than this one here. So we have, there we go. This is sequential search, recursive 3. And let's go to the beginning. And again, this is the same exact code that's from the notes.py. And let's see, so first notice in our stack frame right here, at the very beginning, there are two variables created, xs and y. Xs and y correspond to the parameters that come in for the sequential search function itself. Here, when I call this, or when I define this go function right here, that creates a new variable on the local stack frame that points to the definition of the function. Now on line 15, when I do return go at 0, it's creating a new frame for the local function go. And now this function only has a single parameter I, and this parameter I is the index 0. Now if we walk through, so if I equals the length of x, well, the length of x is, what is it? 6. So 0 is not equal to 6, so that's going to be false. And now here, instead of saying if xs at 0 equals y, I'm saying xs at position I equals y. I is again is 0, so I at 0 is 1. 1 is not equal to 2, what I'm looking for. And so we don't go in there. Whoops. Accidentally jumped us through the whole way, so let's go back to where we were. There we go. This is where we had left off before. We were saying that we had the go function on our stack frame, and I is equal to 0. Xs at position 0 is equal to 1. 1 is not equal to 2, which is what we're looking for. So this is false. So we don't go to this return statement, and we come down here to the recursive call. And now we're recursively calling go. We're calling this helper function, this local function, rather than the global function itself. And so down here, our stack frames that are getting added are stack frames for go instead of stack frames for the sequential search function. Here I'm adding our new variable I is 1. Similarly, it's everything's going to evaluate to false. Comes down here. Let's see, I equals 3, so the value is 4, so it'll still be false. But now I is equal to 4. Xs at position 4 is equal to 2. That is what we're looking for. That is the value of y. So xs at 4 equals 2. That'll be true. So we'll go inside the if statement and hit this return true right here. And now we'll keep going, passing that return true up the call stack and eventually returning true. So the key difference, the key maybe advantage of using this sort of recursive technique is that our go function, our local function, only needs to pass in a number instead of multiple things. It doesn't need to pass then two parameters like a list and the thing that we're looking for. So it makes it a little bit more obvious maybe what is the value that we're recursing on, because there's only one possible value. In the previous sequential search right here, there were two values being passed into the function. So you kind of have to think a little bit more about which one of these is the one that I'm doing the recursion on. With this formulation, there's only one thing that's being passed in, so it makes it a little bit more obvious which one's the one you're doing the recursion on. So that's one advantage. The other advantage is, again, we'll talk about it with the runtimes, but you'll notice that this one avoids having all of those big XS lists down here. So it'll actually be faster and it'll be linear runtime. And this is the function that if you wrote this in Python, it would actually execute the exact same code internally in the and your CPU as if you had done the for loop. Are
I have
there
a
any
question.
questions? Yeah.
I'm not really quite sure what you mean by pass the true back up the call stack. Could you talk about that?
Sure. So let's go to the point where, here we go, we got return true right here. And so yeah, the phrase was pass the true back up the call stack. That's, I wouldn't say that's like a formal phrase that's formally defined anywhere, but that's something that any practicing computer scientist or programmer would understand kind of the intuition about what that means. So I will walk through kind of the intuition about what I meant by that right now. Here, when I said return true, what's going to happen is that, so this return true right here, we're popping off this frame from the call stack, and we're going, so control flow will go back to this frame right here. So I hit next, control flow goes back to this frame right here. Here we had the return go right here. So this go right here corresponds to this stack frame right here. The return value of this stack frame is true. So this go right here just gets replaced by true. And now this one is also returning true. So we'll pop off this stack frame, and this true value will get substituted in this go function call inside of this stack frame, which causes it to return true because we're just immediately returning whatever the previous go said. And this one is, again, just returning whatever the previous go said, returning whatever the previous go said. And now we're on this location here, returning what the previous go said. And it returned true, so we'll return true as well. Yeah, so the phrase of passing up the call stack is just sort of shorthand for saying whatever this return value is, it gets substituted in for the function call right here, and then that line gets evaluated. It's a great question.
And how does that affect runtime at all? Because here you only have like 4 or 5 instances of Go in the frame, but what if you had like thousands?
Yeah, it's a great question. So the short answer is that no, this has the same runtime as the iterative version. They're both going to be linear runtimes. The long answer is that Wednesday we'll discuss this master theorem and be able to actually apply that theorem to prove that they have the same runtimes. And we'll also be able to show that this one here is actually slower. It's a great question, but hold on to it until Wednesday. Any other questions so far? Okay, so what we'll do next is we'll keep scrolling down and we'll take a look at this binary search. And again, this binary search is just absolutely foundational to computer science. I have a couple of versions of binary search here. Here is the iterative version of binary search has to use a while loop instead of a for loop. So again, we mentioned that we have good techniques for knowing what is the runtime of code that uses for loops. But at this point, we have no techniques for what's the runtime of code that uses while loops. And actually, there are no general techniques for this. So when a computer scientist encounters a while loop and wants to know what is the runtime, the sort of standard procedure is you have to convert it into a recursive algorithm and then apply the master theorem on the recursive algorithm. You can see that this program's, we'll go into the details here of what it's doing in a second, but it's a little bit complicated. I don't know, it's 15 lines or so. A lot of moving parts here, and it keeps going. This recursive one, no while loops, still a little bit messy. This is going to be sort of the literal translation of the while loop version into recursive code. And then down here is the simplest recursive one, and you can see that the runtime is, or sorry, the amount of code is much shorter than the previous ones. So this will be the version that we'll start with. It'll be the version that is easiest to understand. Let's see. We have about 10 minutes left, a little less than 10 minutes left in class. So rather than getting started on this, I don't think we'll be able to fully walk through exactly what this program is doing. So I'll save this for walking through this for Wednesday, and we'll talk a little bit about what your homework is for this week. So the homework is posted, and again, up here in this binary search, oops, let me refresh this. Oh, looks like this link is not working, so I'll fix that for you after class, but the link just goes to binary search as the name of the repository. And inside of here is a file binary search.py. And in this file are 3 functions. There's this find smallest positive, count repeats, and argmin functions. We will, you'll have to use the binary search algorithm to solve all 3 of these problems. This find smallest positive function is almost exactly the same as the code that, that I provided in the notes.py file. The exception is that, like I say in this hint right here, instead of having the y as something that's passed in as a parameter, you're just searching for 0. This count repeats is a little bit of a more complicated one that you'll have to work on yourself. And then this argmin one is an even more complicated version. There's also an extra credit one down here. If you, I provide the pseudocode for the extra credit. It uses a variation of binary search called exponential doubling. And we're not going to go over the details of that algorithm in class, but here's the pseudocode. If you implement it, you'll get your extra credit. The test cases for this assignment, still using PyTest like before. And I just want to highlight that the test cases are divided into 2 sections. The top half test cases are all for correctness of your algorithm. And there's quite a few of those test cases. And then down here, this section right here, these are not for correctness. These are for runtime of your algorithm. So all of your algorithms that you implement should have logarithmic runtime. So whatever the n value is, the runtime will be log of n. And here in these test cases, I'm creating some lists that are pretty big, 100,000 elements inside of them. And so if you're not logarithmic, let's see, so log of 100,000 is 5, so that's a really small number. If you're logarithmic, it'll go fast. It'll just take a second to run each of these test cases. If you're not logarithmic, your runtime, instead of just doing 5 operations, it'll do 100,000 operations. It'll be enormously slow, and it'll sit here for hours before it finishes. On GitHub Actions, you have a limit of only 1 hour of computation time for your test cases, and so it'll fail. It'll time out that you don't have enough time to run these test cases if the implementations are not actually logarithmic. Probably these test cases won't come up, but if you're sort of follow the outline of the code in the notes, then it'll be logarithmic. But if you do notice the test cases are hanging, that's what's happening. Let's see, we have a few more minutes. I don't want to talk about any other new material though. So are there any questions that anybody has about the homework or anything we talked about today? Okay, then that'll be it for today. On Wednesday again, we'll actually talk about this binary search algorithm in detail, and we'll use that master theorem to prove that its runtime is really, really fast. And yeah, I'll have office hours now. Stick around if anybody has questions about this or about your homework assignment from last week. I'll be happy to take those then. Otherwise, I'll see you on Wednesday.
Thanks, Mike.